Welcome to IFERP, a forum where innovations and research interest could be supported and developed, prioritizing our mutual interest. In this video, we want you to dive into our world, giving yourself a clear insight into IFERP. But first, who are we and what do we do? Institute for Engineering Research and Publication, IFERP for short, is one of the world's largest non-profitable professional associations operating under the Techno-Elite Research and Development Association, TRADA, meant for research and development in the field of engineering, science and technology. We are one of the largest professional bodies for engineering professionals in India and across the globe, established in 2014. We extend to every part of the globe with more than 28,000 professional members and 34,000 student members. Our growing membership at IFERP has led to an increase in members from Europe, Asia, Australia, Africa and the USA, fostering networking opportunities that strengthen ties within and across countries and technical communities. The mission of IFERP is to connect professionals at an integrated platform for growth to divert knowledge and skills towards the sustainable application of professional education and more. And our vision of digitalizing innovation processes through our professional networking services and more has pushed us forward to our achievements today. With our mission to make our academic services reach the top and grassroots level of institutions, we are funding colleges to organize conferences and scientific events, enabling researchers incubated at different areas of our country to directly contribute towards the transformation of India. IFERP simply connects engineers, exchange global innovation, and acts as a bridge between researchers and academics by organizing international conferences, world conferences, faculty development programs, webinars, seminars, providing membership, and more. Some of our conferences include WCASET Malaysia, WCASET Jakarta, ICAS ETAM APU Malaysia, and many more. We've also organised scientific events in association with renowned universities done in the past, with over 28,593 journal publication services, creating opportunities to get your research paper published in high impact factor journals such as Scopus Indexed, Web of Science, Google Scholar Index journals, ESCI, UGC approved, L Compandax, ISI, Shimago Index journals, and many more. To make our operations smoother and more perfect, we have been supported by our associated organisation, Association of Cloud Technologists, Global Association of Nanotechnology, International Association for Big Data Analysts, International Association for IoT, International Wireless Network Association, and World Association for Structural Engineers. We have also worked alongside several clients and partners both nationally and internationally like University Malaysia Sabah, APU Malaysia, UNJ Jakarta, MC University Thailand, Ajman University Dubai, PUP Philippines, IIUM Malaysia, ISU Philippines, FCPC Philippines, WCC Philippines SRM University, Galgotia University, Amity University, and much more government and private organisations in different countries. At IFERP, we believe that there's always a better way to treat professionals, and that is what we do. If you would like to see more or go deeper on IFERP, you can visit our website at www.iferp.in.
Ma'am, you may turn your video on, ma'am.
Yes, sure.
Yeah. Hi, everyone. Good morning, and I welcome you all to the webinar series on lecture series on machine learning. So we're on day 2 of this 3-day webinar series, and today we will be discussing about linear regression, logistic regression, polynomial regression, and multivariate regression. And an eminent keynote speaker, Dr. Vasima Khan, has joined us for today's session. Good morning, and I welcome you, ma'am.
Thank you so
much for joining, actually.
Thank you.
Yeah, so before we proceed, I'd like to introduce our keynote speaker. Dr. Vasima Khan has been associated with Computer Science and Engineering Department at Sagar Institute of Science and Technology, Gandhi, Nagar, Bhopal, since October 2020. Dr. Vasima is a unique blend of technical expertise with student-focused teaching, a dedicated and hardworking professional who is committed to providing a well-balanced, supportive, and learning environment for all students. She has done a bachelor's, master's, and doctorate in computer science engineering and has more than 9 years of experience in teaching in both UG as well as PG engineering colleges. Dr. Vasima taught various important technical subjects, out of which conceptual skills are operating system, compiler design, theory of computing, databases, and computer architecture. Also, she has taught a few recent subjects like machine learning, deep learning, natural language processing, etc. She's doing significant research work in the area of machine learning, deep learning, GAN, natural language processing, wireless sensor network, and other from the last few years. Dr. Vasima is having more than 16 research papers in national and international journals as well as conferences. She is working on various research projects like intent detection using deep learning and NLP, stock market prediction, fake news detection, and few more. She has participated as well as coordinated various events like faculty development program, workshops, conferences, cultural and sports functions, etc. She also has experience in running an ACM student chapter from last 2 years. So she's always ready to learn, teach, and innovate, as well as tries to incorporate new ways into teaching. So currently, ma'am is an associate professor with the Department of Computer Science and Engineering at SISTEC, Gandhi Nagar. So welcome, ma'am. Once again,
Thank you so much.
Thank you very much for joining us.
Yeah. Thank you so much.
Yeah.
Yeah. Thank you so much for introducing me.
Yeah. You're welcome.
Yeah. Let me start the screen sharing and then start the session. Yeah.
I'll turn off my video, ma'am, so you can take over. Okay.
Okay. Yeah. Sure. Thank you.
Yeah. No problem.
Okay, so is my screen visible, Ms. Nisha?
Yes, ma'am, it's visible. You may proceed.
Okay. Thank you. First of all, I would like to thank Ms. Nisha for introducing me. A very good morning to one and all present over here, and I welcome you all on to the second session of lecture series on machine learning. The topic which I'm going to cover today is linear regression, multivariate regression, polynomial regression, and logistic regression. Okay. So, as I know that in last session, you had the basic of machine learning and supervised and unsupervised has already been covered. But I would like to start with a very, very basic definition of machine learning. And I'll explain and talk about it very briefly. Okay. So in 1959, Arthur Samuel gave this definition of machine learning, which says that ML is a field of study that gives computer the ability to learn without being explicitly programmed. So what does it mean? It means that machine learning is not a technology. Machine learning is not a programming language. Instead, it is a field of study that makes the computer or the machine to learn or perform any task without being explicitly programmed. This means that in machine learning, what we do is we are not going to write a specific code or a specific, explicit code for performing any task. Instead, what we are going to do, we are going to make the computer or machine observe certain data, and on the basis of that observation, it is supposed to perform any task. Okay, so we are going to take many examples which will clear this definition more in our today's session. So the next thing is types of machine learning. Machine learning is categorized on the basis of various factors like human supervision, learn incrementally, how they generalize. So on the basis of human supervision, it is divided into three parts: supervised, unsupervised, and reinforcement. And in yesterday's session, you must have gone through supervised and unsupervised learning and the basics of machine learning. So I'm not going into detail in that. Instead, I'm just going to focus on the topic of today's topic, which is basically regression and classification, which comes under the kind of machine learning, which is supervised machine learning. Okay, so this is basically the categorization of machine learning, which you are seeing on my screen, and we are going to talk about supervised machine learning. So supervised machine learning is basically a kind of machine learning in which there is a specific kind of human supervision. And what do you mean? What does we mean about by this particular thing is that in supervised learning, we are having data, and along with the data, we are having the label, or you can say we are having the desired output. The target output is always given to us, and on the basis of that target output, we are going to perform the task, or we are going to make a model which is going to perform the task. Okay, so let us start with regression. What do you mean by regression? Regression is a machine learning method that allows us to predict a continuous outcome variable y based on the value of one or more multiple predictor variables. See, what is happening in regression? There is a kind of continuous outcome variable. See, just now I have told you that regression is a kind of supervised learning. So definitely there will be a target, there will be a target outcome, there will be a target output with us in regression as well. But what is the main thing, or what is the key point, which is the definition of regression? The key point is that regression is a machine learning method that is basically used to predict a continuous outcome variable. Okay, that means the outcome variable which we are predicting is continuous. For example, you can say that if we are predicting the price of a car given a set of features, okay, then this example will be a kind of a regression. Why? Because we are predicting price, which is a continuous variable. We are predicting price, which is basically a variable which is continuous. What do you mean by continuous? Like it is not having classes, separate classes or groups. Instead, the price is a variable which can change continuously. Okay, so and provided that we are predicting the price of the car given a set of features, and the set of features or the features which are given to us is known as predictors, or you can say independent variables. Okay, so the set of features here is independent variables or the predictors, and on the basis of that, those features, on the basis of the observation of those features as well as the target output, the target price of the car given to us, what the computer or the machine is going, or computer is going to predict the price of the car of a new sample which we are going to give present to the computer. Like the procedure is that we are going to train a model, and during training we are going to present certain features as well as the target output to the computer or to the model, and on the basis of that training, after the training is completed, the model will be able to predict price of car for new examples. Okay, so this is about regression. And to train the model, we have to give many examples of cars, including their predictors and labels. Like it is not like we'll show one or two set of examples of the features and set of the examples of the features and the labels, or you can say the predictors and the labels. We need to give a huge set of examples. We need to show a huge set of examples to the computer or to our model, so that it will be able to predict the price for future examples. Okay, so this will be given as the data set. Like while we are training our model, we are going to give all the data sets. We are going to give all the examples, various examples of the features and various examples of the values of the features and target label to the computer, to a model. And after the training completes, it will be going to predict for a new value. It will be more clear using this particular diagram, which is shown here. This is a graph in which we can see that on the x-axis there is one feature. Like if, for example, if we are taking the example of this predicting the price of the car, then let us assume that there is one feature only, so that we'll be able to see it in 2D. So this is a graph in which the feature is on the x-axis and the value or the prediction or the price of the car is on the y-axis, and these are the points which is basically showing us the set of examples. Like this this particular circle which is shown over here is giving us a value. It is showing us one example out of all the examples which we are using during training. Okay, so these all circles represented over here are the set of examples which we are going to show to our model, train our model on these examples, and then the model, after the training has been done, the model will be able to predict the value for predict the value of the car or the price of the car for new instances. Okay, it is like showing various instances, showing various examples of something or certain thing to the computer and train a model on the basis of those examples. And then after that, we are going to, after that, the model is going to predict the label or the target, predict the output for new examples, for new instances. And in the case of regression, the model, or you can say the thing which we are basically predicting is continuous. Okay, you can see from here this diagram that the label, the output here is the price of the car, and the price of the car will be a continuous variable. Like for example, if the price of the car for a certain certain instance is 5 lakhs, say it is 5 lakhs, and for certain for some other instance it is 6 lakhs. So it is a kind of thing, it is a kind of variable which is having a continuous function. Okay, so this was about regression. Now we are going to start what is linear regression. Till now we have talked about regression, like the first we have started with supervised learning. Supervised learning is a learning in which we are having target output. Then regression is a kind of supervised learning. So definitely, since it is a kind of supervised learning, it will be having the properties of supervised learning. So it must have the target output with us, and the point in regression is that the key point is that the output will be continuous. Now we are talking about linear regression, so it is again a kind of regression or a specific kind of regression in which the output variable is continuous, as well as it will have a linear relationship with the predictor variable. Okay, so linear regression is the most simple and popular method for predicting a continuous variable. For predicting a continuous variable, we are going to use regression, and for that, the most simple and the most popular technique used is linear regression. But this can be used only when the relationship between the outcome or the dependent variables and the predicted variables will be linear. Okay, so if we take a simple example, then we can see that this is a graph same as we discussed before, but here what is happening, that the feature which is represented on the x-axis is GDP per capita. Let us say that GDP per capita is a feature which basically we are using for making a model, and the output variable here is the life satisfaction. So what we are doing here, we are basically making a model which is given various examples of GDP per capita and life satisfaction, and these examples are shown here with this set with the circles which is shown over here. Okay, and using this particular, after observing these examples, we are going to make a model, and we are going to make a model which is basically which will be using using for predicting using for predicting life satisfaction value for new instances of GDP per capita. Okay, so here you can see that the model which is shown here with the help of this straight line. This straight line is basically the model, and here you can see that the model is a straight line. Why it is? Because there is a relationship, there is a linear relationship of the predictor variables, like the independent variables, which is GDP per capita over here, and life satisfaction. Since the relationship is linear, then we will be able to use linear regression, or will be able to make a model which can be shown by a straight line. Okay, so if we are talking about a single feature model, then only it will be a straight line. Otherwise, if we are talking to a scenario where we are having two features, then it will be a straight plane. Instead of straight line, we'll be using straight plane to demonstrate the model. And if we are using more than two number of features, like 3 and more, then we'll be using straight hyperplane. But the key point over here is that the relationship between the predictor variables or the independent variable and the dependent variable will be linear. It should be linear, then only we'll be able to use linear regression. Okay, now see, linear regression is basically, we have seen that in linear regression, the model which we are going to build will be represented by a straight line, or you can say there must be a linear relationship between the predictor or the independent variable and the dependent variable. Then what we are going to use here is that we are going to use an equation, or we are going to use an equation for representing the model or for defining the model. So in this case, since we are having only one feature, GDP per capita, then the equation will be like this: life satisfaction, which is basically our output in this case, it is equals to θ0 plus θ1 into GDP per capita. This is the equation which we are going to use for making this model. Okay, so what this equation is basically mean? This equation is an equation which is basically defining the model, and here life satisfaction is defined in terms of GDP per capita, which is the independent variable for us. So since we are having only one feature or one independent variable, so we'll be using this equation. Here, θ0 and θ1 are the constants, or you can say these are the model parameters, or these are the weights which we need to use appropriately, so that we'll be in a condition where our output will be calculated or predicted accurately on the basis of the feature GDP per capita. Okay, so the main thing, or the concept which we are going to use in linear regression is that we are going to use this equation, or you can say we are going to define this equation. We are going to find out the values of θ0 and θ1, so that the straight line will fit the given straight line will fit the observations, or straight line will fit the the data points which are given to us. Like this equation, this straight line will have this straight line will be defined by θ0 and θ1. So θ0 and θ1 needs to be find out, or you can say will be finding out the value of θ0 and θ1, for which this straight line is best fitting the given data set. Okay, given examples of data set. So here it is found out that θ0 and θ1 for the specific given data set is comes out to be 4.85 and 4.91 into 10⁻⁻⁵. So the equation of this model becomes life satisfaction is equals to the value of theta 0, which is 4.85, plus the value of theta 1, which is 4.91 into 10 raised to the power minus 5 into GDP per capita. So this is how we are going to work in linear regression. Okay, so I have told you what this equation mean. So this equation is basically used for defining the model which is going to predict the values further. After completion of the training, this is going to be used for predicting the values. Okay, so this is the equation we are talking about. So in this, I have told you that this is the values of theta 0 and theta 1. And what is theta 0 and theta 1? Theta 0 and theta 1 are the weights, or you can say parameters of our model, whose value needs to be found out during the training process, and then its value is going to be used after the training is completed. So now, see, this is the general equation of a line, and you will notice that the equation which we have defined just now is analogous to the general equation of a line. Why? Because we are using a straight line in case of linear regression. So its equation in case of linear regression, and that too when the number of feature is only 1. So we are going to use a straight line for our model definition, and then since we are using this, we are using equation of the line to define a model. So the definition of the equation of line of our model is analogous to the equation of a line. Okay, so here you can see that the equation of a line is y is equals to mx plus c. We all know. So what is m and c here? C is the intercept and m is the slope. Okay, so what we need to do is we need to find the value of, I have told you that we need to find the value of theta 0 and theta 1. So in this particular case, in the case of linear regression, in linear regression, we need to find out the value of the intercept as well as the value of the slope for defining the equation which is going to best fit our test set examples. I mean our data set examples. Okay, so this was an example of linear regression where when the number of features or the number of independent variables given to us is only 1. We were having only single feature. Now, what if we are having, and in general scenario, if we are talking about real life examples, definitely any value, any output does not depend on a single value. Okay, and when we are making a model, we need to consider various features, various independent variables. So here I have included an example where we are going to use various features, and on the basis of these features we are going to make the prediction, or we are going to make the model. Okay, so I have taken another example of predicting housing price. If we are predicting housing price, any price of houses, and we are given various features, we are giving the values of various attributes or features of of that particular related to housing price, and here I have specified 4 features, that are longitude, latitude, inhabitants and median income. So if we are given these 4 features, and using these 4 features, if we are going to make our model, we are going to perform linear regression, then our equation will be our equation which we are going to use for defining the model, which this equation will be an extension to the previous one which we have used when the feature was only 1, when we were using only 1 feature. So the equation will become, here the equation will become predicted house price, that is our output, is equals to theta 0 plus theta 1 into longitude plus theta 2 into latitude plus theta 3 into inhabitants plus theta 4 into median income. So I have told you earlier as well that these 4 are the features. So these this will be the values of the features, and theta 0 to theta 4 will be the values, will be the weights or will be the model parameters whose value we need to whose best value we need to find out. Just like when we were having only two weights, theta 0 and theta 1. Here the case will be same as that of the previous one. The only thing is it is extended to 5 features. Why? It is extended to 5 parameters or 5 weights. Why? Because we were using 4 features. When we will be using n number of features, we'll be having n plus 1 number of model parameters, or you can say weights, which we need to adjust so as to find out the best definition of our model, which is going to give us the best results or best predictions of for the new instances. Okay, so the thing is, this was we have discussed 2 separate examples where we have seen that when we are having one feature, single feature, the equation will be, we have seen the model equation. Similarly, we have seen the model equation corresponding to the case where we are having multiple features. So this multiple feature scenario can be extended to a generalized way. So we can define the general equation of linear regression as y cap, and y cap is used for representing predicted values. So the predicted value or the predicted output will be equals to theta 0 plus theta 1 x1 plus theta 2 x2 up to theta and xn. So these x1 up to xn are the features which we are taking into consideration, or which we are having inside a data set. And these are if we talk about the data set in a kind of tabular format, then these x1 to xn will be the corresponding column vectors, corresponding columns of the table of a data set. Okay, so and this n is the number of features. I have told you that we are having n features. So from x1 to xn are the features, and n is the number of features. And theta 0 up to theta n are the weights or the model parameters, in which theta 0 is specifically called as, it is a constant and it is called as a bias or interceptor. Okay, just similarly to the equation of a line, where we basically introduced an intercept or a constant, constants, which gives us the distance of the line from the origin. Okay, so that is same, and theta 0 is basically a bias. Why we are going to add, why we use theta 0, that I'm going to explain you later on. And theta 1 to theta n will be the model parameters or weights, and the feature weights, you can say, or the model parameters, and we need to find the values of these model parameters in order to define a model. Okay, now why are we going to use bias or intercept term in our model, in our model's definition? This is because see, you can see on the screen that 2 examples are given. 2 diagrams are given, and these diagrams are basically showing us why we need to use a bias term. Okay, so let us assume that this red dots or red circles are representing the data sets, representing the examples or the rows in our data sets, and this line, green line, is showing us the model which we are making. So which we have made for this particular data sets on the basis of the training. If we are making this model, then you can see that it is not fitting when we are not taking into account the bias term. Then it is not passing on the examples. Okay, so that means it is not giving us, it is not fitting the examples appropriately. Okay, on the other hand, if we are going to consider the bias term, then the model is the same straight line which we were using in the previous example as well, but the straight line is now fitting the examples very well. Why is it so? It is because if the value of all the features if the values of all the features become 0, then the output will also become 0. Okay, if we are not using bias, you can see from the definition that if we are not using this bias, then if the values of the features, all the features become 0, then the predicted output will also become 0. Okay, so in this case, the predicted output, which will not be up to the mark, it will not be nearby the values which are given to us in the examples in dataset. Okay, so that is why we are going to use bias, and we are going to use add bias to the predicted values or to the target output, so that we can define our model appropriately. Okay, so this is the reason why we are going to add bias. Okay, so we have seen the general equation of linear regression. This is basically the general equation of linear regression itself, but in vector form. Like this is same as that of the one. Yeah, this is this equation is the general equation of linear regression, and this equation is same as this equation. But the difference is here we are using the vector form. We are representing the feature values as well as the weight values in a vector form. So see here we are saying that y cap or predicted value is equals to h theta of x, which is equals to theta t dot x. Here h is basically used for a function which is known as hypothesis, and this is basically we are using hypothesis is a word which we basically use for the function which we are going to apply over the input so as to get the predicted output. So this is basically a model only. You can say that hypothesis or model are synonyms, and theta we are using here, which is the weight vector, or you can say which is the model parameters vector. Models parameter or feature weight are the same thing. Theta is theta, or somewhere you have heard that it is represented by W as well. So the theta or W or model parameter or feature weight, these all things are the same. Okay, so what we are doing here, we are converting, we are defining the predicted value. We are defining the predicted value in terms of vectors like matrices. Okay, so X is basically the theta is basically the model parameters vector, and it is a column vector, and here we have transposed it. So theta transpose is equals to theta 0, theta 1 up to theta n. It is a vector or a matrix that carries all the values of theta. Similarly, X is basically the instance feature vector, which will contain the value of theta 0 to theta n. Like in the case which we were discussed previously, the housing price example, in that case X will be 1, longitude, latitude, and all. And longitude, latitude, all these are the features, and this 1 is just for the bias term or intercept term. This has been added to the feature vector just to incorporate the bias or the intercept term. Okay, so this was about the general equation of linear regression. When we are going to perform the dot product of the feature vector or the feature vector and weight vector, then the outcome, the result will be the predicted values. Because when we are going to perform the dot product of these two things, it will comes out to be the same equation which we have discussed previously. This equation. Okay, when we are going to perform the dot product of feature vector that is containing 1, x1, x2, x up to xn, and the weight vector which is theta 0, theta 1 up to theta n, then when we are going to perform the dot product of those two vectors, we are going to get the equation same as represented here. Okay, so this was about the vector form, or you can say this was about the equation of linear regression, like how are we going to define a model. But how are we going to define a model is what we have seen just now. But the next question is, how are we going to train it? So I have told you that we need to find the best values of theta, if for which the predicted output is as close as that of the target output. This is training of our model all about. Why? Because what basically training means is finding out the best values of theta, or you can say best fit, finding out the model which is fitting the training set in the best way. So what does that mean? That means that we are just finding out the values of thetas, we are finding out the values of the weight parameters, or you can say the model parameters, which is giving us the definition of the model, with definition of a model which best fits the training set. Okay, so in the training we are going to do this thing only. We are going to initialize the weights from a specific value, and then we are going to find out the prediction on prediction using the model which is defined, and then we are going to compare the predictions which we are getting along with the target output, and the predicted output and the target output is compared on the basis of some performance measure, and correspondingly we are going to change the values of the parameter until we are getting the results, until we got the predictions which is which is very accurate, or you can say which is very good in terms of the performance measure which we are using in our regression model. Okay, so the common performance measure which we basically use in regression model is root mean square or mean square, that is root mean square error or mean square error, that is RMSE or MSE. So I'm going to talk about it briefly. How do we train the model? We'll use MSE or mean square error for training the model as performance measure. I have told you this thing just now, that we are going to initialize the values of the parameters, weight parameters, and then we'll make the prediction, and then on the basis of predictions we got and the target output which we are having, the predicted output and the target output are compared on the basis of some performance measure, and if the performance measure is acceptable, then we'll stop the training, and if it is not acceptable, then we are going to manipulate the values of the weight parameters and then do the same process again and again. We are going to repeat this process again and again until we got a value of the performance measure which is acceptable. Okay, so there can be multiple performance measures on the basis of which we are going to train a model, but here we are in case of linear regression, usually mean square error is getting used. So I'm going to explain you a little bit about what is mean square error. So okay, so let us take the example which we have discussed previously of predicting housing value, and understand what is mean square error. See here, there is a graph in which we have taken only single feature which is known as house area in square feet on the x-axis, and on the y-axis we are having the house value, okay, which is the target output in our case. And we have shown here 5 points, which is basically representing the 5 rows, or you can say 5 instances which are given in the data set. Okay, and these 5 instances are represented by these dots here. Now what we are going to do is, we need to find a line which best fit these 5 points. Okay, so how are we going to do that? We are going to do that using using a performance measure which is known as mean square error. And how are we going to evaluate the mean square error? So for evaluating the mean square error, what we are going to do, if this is the line, if this line is basically the model which we have made or which we have defined, then the for the value of housing area, for the value of house, for a particular value of housing area, if we consider the dot 1 here, if we consider the dot 1 here, this dot 1 is having certain value of housing price, that is the actual value, or you can say the target output which we are having. At the same time, which is represented by y1 here, and it is having another, for the same value of house area, we are having the value of housing price which lies on the line, which lies on the model which we have defined, and this particular point is specifying the predicted value. Okay, so these two values, like the actual value and the predicted value, is calculated for each and every value of the feature, each and every value of the housing area, and then we are going to find out the error. And what is error? The difference between the predicted value and the actual value, because we need to achieve the actual, the target value, and if we need to achieve the target value, then the error between the predicted value and the target value needs to be minimized. So this the error is basically defined in predicted value and the target value. Here it is defined as yi cap. Yi cap is the predicted value for ith instance, and yi is the target value for ith instance. So we are going to calculate the difference between these two. Then we are going to square it out. This will be the squared error. Then we are going to take the mean of the square error for each and every instance. Here we are having 5 instances. This is done for all the instances. Here we were having only 5 instances. 5 instances has been represented here. But in actual scenario, we are going to have a lot of instances, lot of rows in our data set. So we are going to calculate the error, squared error for each and every individual instance, and then we are going to calculate the mean of this particular mean of the squared errors, and this is known as mean square error. And now this is how we are going to calculate mean square error. And this mean square error is basically needs to be minimized, so as minimized, and we need to find the value of theta, feature value, feature vectors, or you can say value of theta, that is weight vector, so that the value of MSE, that is mean square error, is minimized, is minimum. Okay, so we need to minimize the performance measure, which is MSE in our case. And how we are going to minimize it? We are going to adopt a certain kind of algorithm for that, and there are various algorithms available for that, in which we'll be able to, which we can use for making the model, or which we can use for training purpose. And few amongst them is gradient descent, or you can say stochastic gradient descent, normal equation, or closed form. But I'm not going to consider all of them here today, because we are not having that much of time. So I'm just giving you the overall description of these topics. So this was about MSE and how we are going to use MSE for training purpose. I've told you that thing. Now, this is nothing but the, the equation of MSE in a vector form, or you can say this is the equation of MSE for all the instances for each and every feature vector. Okay, so if we are having there in our example, we were having only single vector, single feature. This house area was the single feature which we have considered. So that's why we have used only this equation. But in real world scenario, we used to have multiple features. So if we are having multiple features, then what we are going to we are going to use the feature vector instead of a single feature. So here X is demonstrating the feature vector which contains the values of the all the features. Okay, so this is how the generalized equation of mean square error is when we are having multiple features. Okay, so this you can understand the concept of MSE in terms of this as well. This is the definition. This is the example which we have talked about, the housing example, where we were having 4 attributes, that is longitude, latitude, median house value, and median income. So if these are the 4 values which we are taking into consideration, then xi, which we have used here, xi, is basically what it is explaining to us. I is used for representing every row. Like x1 will be 1. If the value of I is 1, we are talking about the first row. If the value of I is 2, we are talking about the second row. So I is used for representing the various rows. Okay, so here one row is shown over here. X1 is representing one row in which the values of the first row of all the values of all the attributes or the features are the values of all the attributes in the first row is represented. So x1 is equals to minus 118.29, which is the longitude value of the longitude feature corresponding to the first row. Similarly, 33.99, which is the value of latitude corresponding to the first row. So these are the values of these 4 attributes given in one row, and the corresponding median house value, that means the target value, which is demonstrated here by y1, is equals to 156,400. So this is the target value which is given to us corresponding to the value corresponding to these values of the features. And what we need to do, we need to find out a model which is capable of predicting the price value corresponding to this input, which is which is capable of predicting a value which is as close as this target value as possible. Okay, so this is what we are going to do when we are going to use MSE. Yeah, while training model, we just have to find theta, okay, which minimizes the RMSE. So this is what I have explained you till yet, that in training, what we are supposed to do, we are supposed to find the value of theta, the model parameters or the feature vectors, which is best. And what does best value of theta means? It means the value of theta for which the value of RMSE or MSE is minimum. So we can use RMSE instead of MSE as well, but if MSE is minimized, definitely RMSE is minimized, and it is easy to handle MSE. That's why we have considered MSE. And there are multiple different performance factors as well, which we can consider. Like here we have, I have demonstrated you the mean square error. Mean absolute error can also be a performance factor, performance measure which can be used. So there are different performance measures which are available, but in case of linear regression, usually MSE is used. That's why I have considered that in my presentation today. Okay, now we are going to talk about a little bit about the implementation, or how we are going to implement linear regression. See, for each and everything, for implementing each and every function in case of machine learning, you can definitely make your own function. You can definitely implement it in your own way. But there is a library which is known as scikit-learn, used as sklearn, which is having very good implementation of almost all the functions and classes of which are used in machine learning, almost all concepts of machine learning. So here I have demonstrated the way in which we can import the functionality. We can import the functionality which is already implemented in scikit-learn for linear regression. So how are we going to import that, and how are we going to use it for training? Okay, so this is a very simple code which I have included here. You can see that I have written from sklearn.linear model import linear regression. So linear regression is a class which is already implemented in scikit-learn.linear model library, and we are going to import this class, and we are going to use this class
Hello? Hello, ma'am, are you there?
Miss Nisha, am I
Hello?
audible?
Yeah, yes, ma'am, yes, ma'am.
Actually, due to some, connection issue.
Okay,
So
okay, no
I'll
problem.
be,
You
yeah,
can,
I'll be continuing from the same point.
yeah, okay, ma'am,
Okay.
sure.
Is my screen visible?
Yes, ma'am, it's visible now.
Okay. So I'll be so sorry for the interruption. I'll be continuing from the same point. So I was talking about the implementation of linear regression from scikit-learn.linear model, which is a predefined library. We are going to import a class which is known as linear regression, and this linear regression class is already implemented. And in this, all the functions which are related to, which are required to implement linear regression has already been implemented. So if we are going to import this class, then we can use all the functions. If we are importing this class, we'll be using all the functions which are already implemented in this class, and using those functions we'll be able to implement a linear regression in a very simple way. So I have created an object of this class linear regression by writing this particular statement lin reg. I have named the object as lin reg, that is equals to linear regression, and then I have used this object for calling a function which is known as fit. It is not mandatory, but it is a common practice that whenever we are going to talk about machine learning implementation, then we'll be using the name of the function. We'll be using a name fit for the function which is basically used to train our model. Okay, I'm just repeating myself because this is very important thing. Whenever we are going to make or we are going to use any function for training purpose, usually the name which is given to this particular function is fit. So I have used linreg.fit, and in this function I have given two arguments. First one is the housing prepared and second one is the housing label. So housing prepared is nothing but the training set after the pre-processing has been done. So since this is not an hands-on session, so I'm not able to show you all the all the coding stuff and all. So but I'm going to give you a very brief idea about the implementation here. So that's why I'm not including the pre-processing and all those things. The only thing here is the only thing which is to be in the key point here is housing prepared is basically our data set, a training set, our data set on the basis of which we are going to train a model, which after the pre-processing has been done. So I have given the name housing prepared to the data set, to the training set after the pre-processing has already been done. So this fit function is going to fit, or you can say this fit function is going to make a model, train a model on the basis of this training set and the target column. This housing label is the target column. You can say target attribute. It is a column in which the target output is given. So we are going to give the data set as well as the target output to our to this particular function, and in return will be this function will be returning to us the model which we can use further for predictions. Okay, so okay, so when we have run the fit function, then our model is ready, and after the fit function is already executed, then you can use another function which is known as predict, and using this function you can simply predict the values for new instances, the values of your output for new instances. So here I have included included a diagram which is showing basically, I've included this table which is showing basically the predicted value and the actual value. So this actual value is nothing but the target values and corresponding to some new examples, and the predicted value is something which I'm going to predict using the same object linreg, which we have used for prediction for fitting. So this object is used, and using this object we are calling predict function on these these examples only, on some some instances, some new instances, and this actual value are our target output corresponding to the same instances which we are using for predictions. Okay, so this is the predicted value for one instant, for 5 instances, and these are the predicted value for actual value for the same 5 instances. So you can say like you can find out the errors of each and every instance, and similarly you'll be able to find out the mean square error. Okay, so this is how linear regression can be performed, and this is all about linear regression. Since this is not an hands-on session, so I'll not be demonstrating the programming part, but I have told you how linear regression in its simplest form can be implemented. Okay, now the next topic which I'm going to talk about today is multivariate regression. Although multivariate regression is just a concept, so I'll be talking I'll be talking about this very briefly, because multivariate regression is nothing but basically a kind of regression or a kind of linear regression in which we are having multiple independent variables. I have told you that the scenario in regression, or you can say the scenario in machine learning, is like that, in which we are having various independent variables, or we are having one or more independent variables using which, or predictor variables using which we are going to predict, we are going to make a model which is going to predict certain values. Okay, so the value or the variable which is to be predicted is known as dependent variable, because it depends on the features. Okay, and the input and the features which we are using for making the model is known as the independent variables. So it is a very simple scenario. If we are having only single input feature, which is shown here in this diagram, then we can say in this equation, then we can say that this particular scenario is a univariate model, or what you are making is a univariate model. On the other hand, if we are having multiple features which we have already talked about, then you can say this is known as multivariate regression, and you're making a regression model, then the model will be a multivariate regression model, because it will be considering various features, it will be considering various independent variables, and on the basis of those independent variables you are going to find out the value of a dependent variable. Here the key point is that there is another category which is known as multiple regression, where the dependent variables could be more. So you can also have a multivariate multiple regression, where there are multiple independent variables as well as multiple dependent variables. So these are just the concept. These are just the concept, or you can say types of regression, and we have already talked about the technicalities of these things. So I'm just going to explain. Explain you the univariate and multivariate regression in brief. So we have discussed this example earlier, in which we are having one single feature, GDP per capita, and on the basis of this GDP per capita, what we are doing, we are calculating, we are predicting the value of life satisfaction. That means here we are having one single dependent variable as well as one single independent variable. So this is the case of univariate regression. On the other hand, we have discussed another example of predicting housing prices, and in this example we were having four features. 4 features means we are having 4 independent variables, and since we are having 4 independent variables, which is more than 1 or 2, that's why this is a case of multivariate regression. Okay, so and here we are having only single output variable. We can have multiple output variables as well, but the concept of multivariate regression is that we are having, if we are having multiple independent variables, then it is known as multivariate regression. So we have already gone through these examples. Yes, the next topic which I'm going to consider today is polynomial regression. So till now, what we have talked about is about those data in which there is a linear relationship between the input and the output. I have told you earlier as well that linear regression is basically used for those scenarios in which there is a linear relationship between the input and the output. But what if we are not having a linear relationship? Then we cannot use a straight line or a straight plane or a straight hyperplane for making the model. So if we are not having that particular thing, if we are not having linear data, really linear relationship, on the other hand, if we are having a non-linear relationship, then what we need to do, we can use polynomial regression then when we are not having linear relationship. What we are going to do in polynomial regression is we are going to use polynomial regression, which basically convert a data from a linear equation, or you can say from a convert a data into another form, into another representation, which will be able to cope up with non-linearity. Okay, so I'm going to tell you how we are going to use polynomial regression. So polynomial regression is basically, let us take an example where we are going to fit a non-linear data which is basically defined in using a quadratic equation. Okay, instead of a linear equation, a straight line, it is we are using a quadratic equation for defining a data. Here you can see that if we are having this kind of a graph in which a model represented by this red curve is represented by this red curve is basically it is a graph which is showing which is showing us how quadratic equation can be represented using a graph. Okay, so if our data is like, if our data is having non-linear relationship, means that if your data is this kind of we are having a kind of data which is basically, when we are plotting that particular data, we are having we need to make a model which should be represented by a quadratic quadratic equation instead of a straight line. Like if we need to make a model which is shown here by red curve, then we need to use polynomial regression. So we can use a linear model to fit non-linear data. The key point here is, for regression purpose, we are going to use the same linear regression. Okay, the only thing is we are going to convert a data, a non-linear data, into a form using into another form on which we can perform linear regression to handle this particular thing. Okay, so we can extend the concept of linear regression, linear model. We can train a linear model on the extended set of features. The key point over here is that I have told you that we are going to convert our data into a non-linear data into another form. So what are we going to do? We are going to extend the set of features. So how are we going to do? We are going to basically, if you are having a feature A, okay, or you can say if you're having a feature, say let us take any example. Let us take an example of estimating the weight of somebody. Okay, then if you are estimating the weight, then then the height can be an important feature. So if we are having a feature height, then what we are going to do in polynomial regression, we are going to consider height as well as height square. Understood. But why? Because we are basically converting data into a form which can be used for implementing non-linear relationships, right? So this I'm going to explain you. See, this is the equation which basically, this equation is basically getting used for generating some non-linear data. For example, I mean, you can think of it as you're generating some data which is non-linear. Okay, so for generating non-linear data, you need to use this equation. Okay, or you can say that I have used this equation for generating non-linear data. Okay, so if I have used this equation for generating non-linear data, and if I have plotted the graph between x and y, like the input and the output, where x is the feature, is the single feature which we are taking into consideration, and y is the output or the target output, you can say, then y we are generating using this equation, and then if we are plotting, it comes out to be like this graph which is represented over the screen. Now you can see that if you are going to make a model which is represented by a straight line, then do you think that straight line model will be able to fit this particular data properly? No, it will not. It will definitely not, because this data set is basically of the form. For that we need to use some model which cannot be which is represented by some graph, or which is represented by some curve instead of straight line, or I would rather say a quadratic curve instead of a straight line. Okay, so what you need to do, you need to transform the training data into another form, and for transforming the training data into another form, what we are going to use something which is known as polynomial feature. And polynomial features is basically again, I'm using the same library, scikit-learn, which I have told you earlier. We have used the class linear regression for implementing linear regression in which is implemented already in scikit-learn library. So similarly, for implementing polynomial regression, or you can say for transforming a normal data, a data into another form which can be used for for polynomial regression, we are having a class that is known as polynomial features. So this class is basically used for transforming the training data into its square, or you can say to any degree you can extend it. Okay, I have taken the example of quadratic equation. That's why I have written that we are going to add the squares of the features, but we are going to we can extend the data up to any degree, up to 3rd degree, 4th degree, or any number of degrees. Like then whatever you're using the degree, you'll be extending your equation up to that level. Like if you're using 5 as your degree, then you'll be extending your data into another form in which your data can be represented using an equation which is of degree 5. Okay, this is the simple this is the simple explanation about polynomial regression. So how are we going to perform that? So again, we are going to import polynomial feature class from sklearn.preprocessing, and then we are going to make an object which I have given name poly_features of polynomial feature class, and in this you can specify the degree which you want. Okay, if you want to extend your data to degree 2, you can mention here degree is equals to 2. You can mention you can extend your data up to any degrees. Okay, so whatever degree you want to extend your data to, you can specify that particular degree over here. And then include bias equals to false. I have used another attribute. Now, this poly features is the object, which is object of this polynomial feature class. So what I'm going to do here, I'm going to use a function which is known as fit underscore transform. So I have told you that fit is basically a function which fit is a name that is given to functions which is basically performing the training part. Here, fit transform is another function of this particular class which I'm going to use for converting our data into for transforming a data into degree, converting or transforming a data into a form where its degree is converted to 2. Okay, so we were having simple linear data, and now we are extending a data to non-linear. Okay, so here what I'm doing, I'm giving my input x, and x is the data which we have, we have used for construction for x is the data, x is the feature which we have used for making the target output as well. So I'm giving this x as input to the fit transform function of polynomial feature class, and then after this we'll be getting the data which is transformed into degree 2 form, and then this x poly will be the data which we are going to use for in linear regression for training. Okay, so this is just this code is basically this code, and you can say this polynomial feature class is basically just converting a data into from one form to another form. It is not doing the regression. It is not training our model. It is not making the model. It is just transforming a data from one form to another form. And then this this transformed data we are going to use for the regression thing. Okay. Here you can see that x of 0 is this and x poly of 0 is this. Why? If we are having x as input, if we are having a single feature x, and we are defining the degree as 2 in the polynomial feature class, okay, and so when you'll be this x poly will be having 2 values corresponding to the same thing. Why? Because x was the single feature which we were using, so we and we have used degree 2, so x and x square, both of them will be considered both of them will be there in the transformed output. Okay, so here you can see that if the 0th row of x 0th row of the previous input was this, previous data set was this, and then this in the sense was having only one single value, the corresponding transformed output, the corresponding transformed data set is having 2 separate values. Okay, so this is because we are adding x square as well to the transformed data set. Okay, now we are going to apply linear regression over this transformed data set. You can see, yeah, let me explain you this first, then I'll go back to the thing. So linear regression is equals to lin reg is equals to linear regression. This is same as that we have done previously. We are just creating an object of the linear regression class. Now we are going to call the function fit, but in fit function we are passing x poly as the training data set, which is the transformed data set which we have transformed using polynomial features. Okay, and then after fitting this, you can see that you can predict the values as well. Here you can see that I have printed the values of its intercept and coefficient. So intercept is bias and coefficients are the weight vectors. So you can see here that these are the things which I'm getting. So this is I'm getting as the output. So here you can see that it is outputting and 2 arrays basically. The first one is containing a single value, which is basically the value of the bias, which is 1.78 in this case, and then the other 2 things are the coefficients, or you can say the weight parameters, the model parameters. So these 2 values, there are 2 values coming. If we have given the original data in this fit function, then the value value of weight parameters, like model parameters, will be there'll be a single value. There would be a single value corresponding to the model parameter. But here we are getting two values. Why? Because we have extended the data set. We have extended our linear data to degree 2. That means we have transformed the data into a form in which into a 2-degree form. Okay, so that's why it is looking like this, and the equation corresponding to this will become the model estimation, or you can say the model will be defined by an equation which is written over here, like y predicted is equals to 0.56 x square plus 0.93 x1 plus x1 square plus 0.93 x1 plus 1.78. x1 is the single feature which we were having in our original data set. Since we have transformed it into another form, then x1 and x1 square both has been added to a data set, a transformed data set. That's why we have got these two weight parameters, 0.56 and 0.93, and this is the intercept 1.78. So that is why this equation, the equation of the model becomes of degree 2. Okay, so this is how polynomial regression has been done. One more thing I would like to tell you is that if you are using a polynomial, if you are transforming your data in using polynomial features, and if you are specifying the degree as d, and if you are having n features, then the transformed data will be containing n plus d factorial divided by d factorial into n factorial number of features. Okay, the number of features will be there in your transformed data will be this much. Okay, so where n is the number of features which you are having in your original data, and d is the number of degree which you have mentioned during polynomial features. Okay, so in our case you can check that since we are having n as 1 and d as 2, then it will become 1 plus 2, that means 3 factorial divided by 2 factorial into 1 factorial. That will give us the value of 2. Okay. Okay, so if we are having two features A and B, then, and if we are giving the degree as 3, then it will become the features in the resulting data set will be containing, in addition to A and B, it will be containing A square, A cube, B square, B cube, AB square, and A square B. Why? Because you have given degree as 3. So in this case, n is equals to 2 and degree is equals to 3, d is equals to 3. So it will become 3 plus 2 factorial divided by 3 factorial into 2 factorial. So it will become, the number of features you can calculate using this formula. Okay. So this was about polynomial regression. Now, I have told you, I have presented out the the sample data set which we have created using a polynomial, using a quadratic equation, and the data set is represented by like the target outputs or the target values were represented by these blue dots. And what we have created, when we are going to plot our model, which we have created just now using the scikit-learn functions, if you are going to plot that model, it will comes out to be like this. Like the polynomial regression model will become like this, will be represented by, if we are going to represent it using graph, it will comes out to be like this, which is demonstrated, which is represented over the screen. So now you will be able to understand why we have converted our linear data into some other form, and then we have implemented the linear regression over it, because we need to find a model which should have a greater degree or a higher degree than 1. Then the linear, if in spite of using, in spite of generating a model which can be represented by a straight line, we have to we have to extend it into some higher degree. And in this case, I have taken an example of quadratic equation. You can extend the degree up to any level, whichever you want to. Now the question came, why are we going to use polynomial regression, and when are we going to use polynomial regression? We are going to use polynomial regression when we are, in general scenario, there is, you will not be able to look your data in this particular format. Why? Because in real world scenario, there will be plenty of features, and it is not possible to demonstrate plenty of features in using a graph, and then you'll not be able to understood. You'll not be able to figure out which degree model you should make. So basically the thing is, there is a key concept that if you are making a model which is underfitting, I hope all of you must be knowing the concept of underfitting and overfitting, but if you're not aware of it, I'm just going to explain you it in very briefly. Overfitting is a case in which your model is basically taking into account each and every instance. Okay, like it is going exactly as it is going exactly. Let me show you one thing. Let me demonstrate it using a pen and pencil. If you're having a graph like this, and if there are certain points like this, if there are certain point like this, and if your model, if you have made a model which is basically covering out each and every data point, and which is trying to cover each and every data set exactly, then you can say that it is overfitting, because this kind of model cannot be generalized, and if a model cannot be generalized, then it will not be able to predict actual or correct values. On the other hand, if you are having, and this is known as overfitting, like your model is overfitting the data set. On the other hand, if you are having another kind of scenario in which this is the data set which you are having, if this is the data set which you are having with you, then if you're making a model like this, so do you think this model will be able to, this model will be able to predict the values, right? No, it will definitely not. So if you are having this kind of data, you'll be required to make a model like this. Okay, so this is underfitting, like your data is not at all giving accurate results. Underfitting is a scenario when your model is not at all able to predict predict the value, the target output at all. Okay, so that is a kind of underfitting. So underfitting happens when you're having very less data, or when you have just started training your model, then at that point of time underfitting occurs. But at that point of time underfitting occurs. So basically my point here is, let me start the screen sharing. Okay, so is my screen visible, Miss Nisha?
No, ma'am, only the whiteboard is still visible.
Oh, no, I have started sharing my screen. Okay, let me do it again. Let me do it again.
Yeah, okay.
Is it visible now? I have shared all of my screen.
I'm still able to only see the whiteboard, ma'am. Have you like closed the app completely?
Yes, I have closed it.
Okay, maybe like turn screen share off and turn it on again. Maybe that will work.
Yeah. I'm doing the same thing only. Is it visible now?
Yes,
Okay.
it's visible.
Let me go to the slide I was talking about. Okay, so we were talking about underfitting. So this was about overfitting and underfitting. So underfitting happens when is not capable to predict accurate value at all. Okay, so when underfitting is happening, when our model is like not able to predict values accurately, then underfitting happens. And when underfitting is happens, we need to, it is a good practice to use polynomial regression, because because if we are using polynomial regression, it will increase the degree, and it will overcome the problem of underfitting. Okay, on the other hand, if your if your model is overfitting, like it is over remembering or over predicting the values, then you can say if it is trying to by heart everything, then that is the case of overfitting. So in that particular case, if your model is suffering from overfitting, then you need to reduce your degree in polynomial regression. If you have used polynomial regression, then you need to reduce your degree, or you need to go back towards the linear regression. And this is the case of overfitting. So this was about polynomial regression. Okay, so next I'm going to start talking about logistic regression, which is basically a kind of implementation, or which is basically a machine learning model, which is basically a machine learning technique, or you can say technique for creating machine learning model for implementing linear classification, or specifically I would say linear binary classification. So since we have talked about classification here, and in logistic regression we are going to implement classification, so let us have a brief introduction to what is the concept of classification. So I have told you that supervised learning is having two main techniques. First is regression, which we have discussed so far, and the second is classification. So in regression, we were having the output variable was a continuous variable, like the output variable will be a continuous variable. On the other hand, in classification, the output variable is not a continuous variable. You need to identify the label, or you need to identify the class in which a certain input belongs to. Okay, so if the data set, the data set will be having various rows, and corresponding to each and every row, since it is a supervised machine learning technique, then it will have the target output. But here the target output is not continuous. On the other hand, the target output is basically the classes. Okay, like the target output will have labels, the desired solution, which is known as labels, and that label will tell us the name of the class to which that particular instance belong to. Okay, so sorry. So this is the case of classification. We can say that we can look at some of the examples of classification. A spam filter is a very good example of classification. Why? What is basically a spam filter? Spam filter is a software that is classifying the email which are coming as spam or not spam or ham. Okay, so since this spam filter is basically what it is doing, it is having two classes, spam and not spam, and it is just predicting that whatever the email is coming, whether that email belongs to spam class or not spam class. So it is an example of classification, because here it is predicting an output, it is having the target output, but the target output, the target classes are very well defined, but the target classes are not, the target variable is not continuous. The target value variable is having various different classes. Here the number of classes were 2. Okay. Now the same thing I have already explained you. Spam filter is a software which will, you know, identify whether an email is spam or not. Another example of classification could be finding out, recognizing handwritten digits. Okay, so if we are doing that, and if we are recognizing a digit and finding out whether that digit is 5 or not 5, then this will be an example of classification only, but this will be an example of binary classification. Why? Because we are having only 2 classes. Classification in which the number of target classes are target classes is 2. It is known as binary classification, and when the number of classes is more than 2, then it will be known as multi-class classification. Okay, so here the digit recognition classification task can be of multi-class classification as well. If we are recognizing what digit it is written, like if it is the handwritten digit, if we are doing the task of recognizing the digit, then it is known as multi-class classification, because that digit can be one among the 10 classes from 0 to 9. Okay, so there will be 10 output classes. On the other hand, if we are talking about this particular example which is shown over here, where we are recognizing that whether a handwritten digit is 5 or not 5, this is a case of binary classification, but both the examples are examples of classification itself. Okay, so another example of classification is classifying flowers of a particular species, like iris data set. See, there is a kind of data set which is very well known and popular when we are dealing, or when we are, you know, understanding the implementation, when we are trying out the implementation of classification. Then there is an important or popular data set that is known as iris data set. And what iris data set is basically about? Iris data set is containing the features of flowers and and corresponding to the those features of flowers, it is telling that whether that flower belong to to which category this particular flowers belongs to. And in this iris data set, we are having 3 labels, like we are having 3 classes of flowers, 3 kinds of flowers, which is known as versicolor, virginica, and setosa. So these are the 3 classes to which any flower will belongs to. Okay, and what kind of classification is this? This is a multi-class classification. Why? Because we are having 3 classes, which is more than 2. So that is known as multi-class classification. So these were some examples of classification. I'm not going into detail of types of classification again, because we need to talk about logistic regression. I'm just telling you here what are the basic types of classification. The binary and multi-class, I have already talked about binary and multi-class just now. There are 2 more classes of classification, 2 more types of classification. One is multi-label and another one is multi-output. So multi-label classification, when you're having more than one dependent variable, when you're having more than one labels, you can say. Label is in this case, the label was type of flower. Okay, flower belongs to which type. So the type of flower was the label in iris data set. So if we are having more than one labels in any classification task, then it will be known as multi-label classification. And if we are having multiple label and in together with that we are having multi-class in each and every level. Okay, then it will be known as multi-output classification. Like multi-output classification is a combination of multi-class and multi-label classification. Okay, so now we are going to discuss about what is linear classification. So I have told you just now that in classification we are having separate classes and we need to determine to which class our input belongs to. So here I have taken an example of the same data set which we have talked about, iris data set, but I have limited the constrained the classes to 2. Here I am considering only 2 kinds of class, versicolor and setosa. Originally in iris data set there are 3 kinds of class, there are 3 labels, but here to demonstrate using on a 2D platform, I am considering only 2 types of class, that is versicolor and setosa. Now if we are having data set which is represented here by this blue squares and yellow dots, okay, so what we need to do here is that these are the rows or instances in our data training data set. Now you can see that this yellow circles and blue squares, these all are nothing but instances in our data set, okay. But from here you can see that if I am plotting these data set over 2 features which I have taken into consideration, that is petal length and petal width. If I talk about iris data set, there are 4 features: petal length, petal width, sepal length and sepal width. But I have considered only 2 features here, which is petal length and petal width. So here if I'm plotting these instances on a graph on which I have taken these 2 features on x-axis and y-axis, then it comes out to be something like this, okay. And what I'm supposed to do if I'm performing classification task, what I'm supposed to do, I'm basically trying to make a model which is capable enough to differentiate among these 2 kind of classes, okay. This yellow circle is representing setosa. I mean, this yellow circle is representing those instances for which the target output is setosa. On the other hand, this blue square is representing the set of instances to which the target class is versicolor. Okay, so my aim is to make a kind of line or a kind of my aim is to make a model which is capable of differentiating these 2 kinds of flowers. Okay, so classification is this task, and if we are able to do it using a straight line, then this will be straight line or straight plane or straight hyperplane. This will be known as linear classification, same as that of the case of linear regression. If if we are able to make a straight thing, if we are able to make a straight line, if we are able to use a straight line which is capable enough of doing that particular task which is capable enough of doing the classification task, then we can say that this is a linear classification. Now here you can see that we have used 3 models. We have implemented here three lines have been represented here. One is green, second is red, and third one is pink. These lines are nothing but the models which we could try. These are the models, or you can say decision boundaries, which we can use we can use as a model in case of classification. So you can see that if this green line is using as a model, it will be very bad model because it is not able to classify at all. And this pink and red line also, these are capable of classifying, but these are also not very good model. So although these are basically defining the decision boundary on the basis of which we can classify classify our data. This is about the iris data set. I have told you earlier as well. Now, this I have taken into consideration. I have told you that there are 4 attributes or 4 features inside iris data set, but I have considered only 2. You can take any 2. And then flower type is again, there are 3 types of flowers, but I have taken into consideration only 2 flowers. Okay, so if we are in a condition that we can use a straight line, then it will be known as linear classification. This will not be the case for each and every type of classification. Okay, so now logistic regression. What is logistic regression? Logistic regression is basically a very common commonly used machine learning algorithm which is capable of implementing binary classification problem. I mean, you can say that logistic regression can be used for multi-class classification as well, but in its that is, you can say that is an extension of logistic regression. That is an extended usage of a logistic regression. Logistic regression is basically a very simple method, a commonly used method, which is introduced, or which is in its basic form used for implementing binary classification problem, like the problems in which there are two classes and we need to make predictions that whether the given input belongs to which one out of them. Okay, so this is about logistic regression. Now, what is basically, why it is known as logistic? Logistic regression is known as logistic regression because since it is an extension of linear regression, first of all, and secondly, it uses a function to transform the output into its probability, and that function is logistic function. Logistic function is a kind of function whose definition is represented over here. Here you can say that logistic function is having the definition 1 upon 1 plus e raised to the power minus t or minus x, whatever input you're giving. So what we are doing in logistic regression is that the output value which we are getting after performing the regression task, or after making any model, after developing any model, if we are whatever value which we are getting of output, we are converting it, we are applying this logistic function over that particular output and transforming it into the probability, and then we are classifying it, because we are I mean, if the probability, after applying logistic function to the output value, whatever is coming is the probability, and if the probability is greater than 0.5, we are classifying it as one class, and if it is less than 0.5, we are classifying it in another class. So this is how we are basically doing logistic regression. I mean, what is the logic behind logistic regression? I have told you just now this thing. Now, again, for illustrating logistic regression, I'm taking the same example of iris dataset, which I have explained you just now. So iris dataset, I have told you that it is having 3 classes or 3 flowers, and there are 150 instances, 150 rows available in this dataset. Okay, so this I have already explained you. This is a little, this is a briefing about the iris dataset. There are 4 features like sepal length, sepal width, petal length, and petal width. The classes are, there are 3 kind of classes. Setosa, versicolor, and virginica, and these are the instances. There are 150 instances in this data set. So this is a code in which we have imported the data set, iris data set, and iris data set is if you are downloading if you are importing the iris data set using this using scikit-learn, then the data set which you are getting is if you are using this particular code which is written over here from sklearn import dataset and dataset.load iris. If you're using this particular thing, you'll be getting the iris dataset as a dictionary, okay, and that dictionary will be as a list, and that list will be having iris dataset will be in the form of dictionary, and that dictionary will be having various keys as data, target name, description, and feature names. So this is something where all the detail about the data set will be there, and the overall data set which we require will be in the key data. So here I'm representing the iris.data, that means the key data of iris data set dictionary. It will be it will be like this, where the values of the 4 features corresponding to all the instances have been given. Okay, so this will be in the form of NumPy array. Again, since I'm not doing a hands-on session on this, so I'm not telling you from the programming point of view, but I'm just giving you a brief introduction to its implementation. Okay, so this was all about the iris data set, how you're going to import it and how you're going to see all its keys. Now, when we are going to use logistic regression, again, there is an already implemented function named as logistic regression inside scikit-learn. So you can import this logistic regression, and then you can use its object. You can create its object, and you can use its object for calling the fit function. And in fit function, whatever data you're giving, the model will be trained on the basis of that data. X is the here X, we are giving the iris data set, and Y we are giving the target of the iris data set. So the model is fitted over this iris data set. Now see, when we are doing a logistic regression, in addition to the function predict, there is another function known as predict proba, and predict proba is going to predict the value, the probabilities corresponding to the probabilities as well corresponding to the values which is being predicted. Like if you are using dot predict function, it will tell you, it will tell you the class to which this particular instances belongs to. But if you're calling predict proba, then it will tell you the probability, which is the probability with which the instance belongs to that class. Okay, so you can find out the probability as well in this. And now this is a function, this is a graph which I have plotted for this particular iris data set only. What I have done is I have taken one feature petal width, and I have plotted the probability which I'm getting against this petal width. Now you can see that this, one kind of instance, one kind of class which is Iris virginica is basically represented by green triangles, and another the second class which is virginica is which is not virginica is represented by squares, okay, by blue squares. Now I have plotted this particular thing in which I have plotted all the probabilities. Now you can see that this iris, this green model shown by green line is basically for iris virginica, and this line curve shown by blue color, it is dashed blue color, this is for not iris virginica. Okay, now the thing is, in case of logistic regression, we are basically of course we are using logistic functions, so we are converting the output output values into probabilities, and we have plotted the probabilities. But the key concept here is we are basically doing the task of classifying. We are not doing the task of regression. Instead, we are doing the task of classification. So we need to classify among these two. We need to classify the overall scenario, or we need to classify the training instance into two or more classes. Here we are classifying into two classes, like virginica and non-virginica. So we are classifying, if we are classifying, we need to find something which is known as decision boundary. And when we are able to draw the decision boundary, what we are doing, we will be taking, all the new instances which is on one side of the decision boundary will be given one class, and all the instances which are all the new instances which will be lie on the other side of the decision boundary will be predicted as the another class. Okay, so this is basically about logistic regression. And here I have told you all these things, like this is for virginica flowers which are shown, which are basically showing virginica flowers, and this is the flowers blue. So blue squares are representing the flowers which are non-virginica flowers, and this is we are having this, this is the portion where overlapping is done. But since overlapping is done, so, overlapping is there, so a little bit of complexity will be there, a little bit of wrong predictions will be there. But again, if we are able to find if we are able to train a model accurately, properly, if we are having different kinds of instances in our training data set, and during training if we have used an appropriate and a strong model, will be in a condition to find out the decision boundary properly, which will be able to classify the instances accurately. Okay, so this was all about logistic regression and how you're going to implement logistic regression. I have told you, I have shown you, the portion where I have created this log reg, that is an object of the logistic regression class of scikit-learn, and we have fitted the data over it. And here you can see that I'm doing prediction over one single instance. I'm giving a new instance whose values of two features are given to the predict function, and this predict function is going to give us the class. Predict function is going to give us, the probability of this new instance. I mean, the probability with which this new instance belongs to a certain class. So it is giving us an array which is containing two values, 1 and 0. That means that this instance is belonging to the class 0, not the class 1. I mean, it is belonging to the class 0 with 1 probability. With 100% probability, this instance belongs to belongs to the 0th class. Okay. So this was about the implementation of logistic regression. Okay, so this I have told you. Yeah, I have shown you three boundaries, I mean three models earlier of classification in this same data set as well. But I have told you that those models were not good. Why? Because those models were not, they were able to classify it, but those models were very, I mean, that was in a direction in which it was not very much appropriate. Why? Because it was very close to certain instances of the data set. Okay, so this is a diagram which is showing us a decision boundary which is very good with regard to the problem statement which we have discussed. Okay, so I think this is all done. Now, the last thing which I need to explain today is the performance metrics or performance measures, which we basically use in case of classification. In case of regression, I have told you that we usually use mean square error or mean absolute error. I have demonstrated mean square error as well. In case of classification or when we are doing logistic regression, the accuracy is not, the error cannot be determined. Why? Because we are not finding out a particular value. Instead, we are finding out whether a particular input belongs to to which class a particular input belongs to. So in this scenario, there could be, we can find out the accuracy as well, but the accuracy is not a very good performance measure. We are having different performance measure to find out, the performance of, our model which we have made. Okay, so there are various performance metrics. I have demonstrated here. Accuracy, I have told you already. Now, confusion metrics, precision, recall, F1 score, ROC curve. There are various performance measure which can be used as, as a matrix for determining the performance. So these are some performance metrics which I have included over here. But I'm not going into very detail of each and everything because it will take time, and we are short of time right now. So I'm just telling you what is all these performance metrics. Confusion metrics is basically a kind of metrics which tell us how many instances we have, it tell us how many instances we have classified properly and how many instances we haven't classified properly. Like if we are having two classes, class A and class B. So confusion metrics will tell us how many instances which are actually belonging to class A and predicted as class A only, and how many instances which actually belongs to class A we have classified it in class B, and vice versa. So this is a kind of matrix which is known as confusion matrix, and we are considering 4 factors here. The first one is true positive. True positive says that we have classified an instance correctly. Okay, like if it was supposed to that particular instance belongs to a certain category and we have classified it correctly. Now if certain instance does not belongs to a class and we have predicted it to be that particular class, then this will be known as false positives. Okay, this will be known as false positive, where we are classifying a particular instance into a certain class, but that instance does not belong to that particular class. Now if we are classifying that this particular instance does not belong to this class, but it actually does, then this is known as false negative. And true negative is actually it was belonging to that class, and we are predicting that it is, actually it does not belong to a certain class, the instance does not belong to a certain class, and we are predicting it correctly. Okay, we are predicting it correctly that it does not belong to that class. Okay, so for having a good performance corresponding to a model, we should have a performance matrix, or we should have a confusion matrix which is having large number in its diagonal. Okay, so let me show you very quickly this confusion matrix corresponding to the 5 and not 5 classifier, which I have given you an example of. If we are determining a handwritten digit, if we are classifying a handwritten digit, that whether this digit is 5 or not 5, then we'll be making this confusion matrix in which this column, there are 2 columns corresponding to the 2 classes. Similarly, there will be 2 rows corresponding to the 2 classes. Now this particular, let us start with true positive. This is true positive. There is a number written over here, that is 4344, which is the number of instances which is correctly classified as 5. Okay, and 53272 is the number of instances which is correctly classified as not 5. On the other hand, 1307 is the number of instances which is which is classified as 5, but it is actually not. On the other hand, 1077 is the number of instances which is actually belongs to 5, but we have predicted it as not 5. Okay, so this is a kind of matrix which we form about our net model, and we will be using this model, this matrix, as a performance measure. Okay, so I'm skipping this part because we are not having that much time. The next 2 performance measures are precision and recall. So precision is basically like how much accurate result we are giving, like the total number of positives, the percentage of true positive with respect to the total number of positives we are classifying. And you can say that precision is basically the measure of how much positive how much accurate positive results you are predicting, your model is predicting. And recall is whatever it is learned, how much of that it is able to predict accurately. So this can be found out using this formula, in which we'll be taking the percentage of true positive with respect to total true positive plus false negative. Okay, so again, precision and recall both should be high, but the thing is for good performance both should be high, but both are inversely proportional to each other. So it cannot be the case when both can be made high. So we need to find a balance between precision and recall, and for that we usually use another, usually use another score, that is known, another performance measure that is known as F1 score, which can be which is having a formula 1 upon precision plus 1 upon recall. It is basically used because it is a measure of how close recall and precision are to each other. Like we need to have recall and precision which are close to each other for having a good performance. So that is measured by F1 score only. Okay. Now ROC curve is a kind of curve which we basically find out, which we basically plot, which usually plotted true positive rate, that is recall, true positive divided by true positive plus false negative, versus false positive rate, and false positive rate is false positive divided by false positive plus true negative. So although there are much background and there is much detail about these things, but I'm not since we are short of time, so I'm not able to explain you all of it. I'm just going to demonstrate you what an example of ROC curve. The thing with ROC curve is that the more it is far away from this diagonal, the more is the area under the curve of this ROC curve, the good the performance is. Okay, so we need to have an ROC curve corresponding to a model. We need to have a model corresponding to which the ROC curve should be like that. Its area under the curve should be as much as possible. Okay, so this was all about the performance metrics. So I hope all the things must be clear till now, and this is all about today. This is all from my side, and I'll be ending my presentation. So if there is any kind of queries, you're more than welcome.
Thank you, ma'am. Thank you very much for the lovely presentation.
Thank you so much. Thank you, IFERP. Yeah, thank you, IFERP, for calling me, for inviting me for this presentation.
Yeah, thank you so much, ma'am. So with this, we reach the end of today's session.
Okay.
We do have the last session of this webinar series tomorrow. So thank you once again, ma'am, and also thank all the attendees who have joined us now. I hope it was very useful for all our participants and informative as well, and they grabbed as much as they can. So thank you once again, ma'am, a lot. And I'd also like to thank our academic partner, United Innovators. So if you need help with the paper publication, patent filing, and research article writing, please do check out unitedinnovator.com to know more about the services they offer. And also, you're free to write to us about the feedback, queries, or questions to webinar@iferp.in. Please do follow IFERP on social media to know more about the upcoming webinars. So thank you so much, ma'am, once again.
Thank you so much.
Yeah. Have a good day, ma'am. Yeah, bye.
Okay, thank you. Bye-bye.
Bye.